Back, everybody. Just checking, Felix, can you hear me? I do not hear from Felix. Can anybody else hear me?
Yes, hello, it's Didier. Etienne, I can hear you well.
Thank you, Didier. Let's continue. So just before the break, we finished the strong duality theorem. And the key sufficient condition for the strong duality was this kind of exotic request that this specific cone is closed in the weak in the weak topology of the duality in the right space. So I mean, this looks like does not look like something you can work with. So before going any further, I just want to maybe just take a step back and go to the more familiar Euclidean space and look at what is the implication of this strong duality theorem for semi-definite programming. So in semi-definite programming, so we are back in Euclidean space. So the vector spaces E1 and F1 are both just the symmetric matrices. The cone that we are working with is the cone of parts of semi-definite matrices. Again, the duality in question is just the inner product, and this is the Euclidean inner product between symmetric matrices, which is also known as the trace inner product. So I think many of us are very familiar with this setting. Also, for the dual problem, we will have the spaces E2 and F2, and they will coincide, and they will just be Rm. And the duality there is just going to be the Euclidean inner product in Rm. So for x having components psi I to psi m and y eta 1 to eta m, this is just the familiar Euclidean inner product in Rm. And so because there's really no risk of confusing these two dualities, or more precisely these two inner products, I will just drop the 1 and the 2, because it will be clear when we are talking about matrices, or we're going to be talking about vectors in Rm. Okay, so we also need this linear transformation that defines the constraints Ax equals to B, and the usual way that these linear transformations are given in standard form is that we are just given some elements of the right space, in this case symmetric matrices AY to AM, that are just fixed, so this is just data, and AX will then be this Euclidean inner product of A1 of X up to AM of X. So again, this maps the symmetric matrices to Rm, and then we will have a dual operator that will map Rm to the symmetric matrices, and this is given by the operator A star, and it maps a vector Y with these components to this matrix. Okay, so this is just the sum of a linear combination of symmetric matrices. So indeed, this is as it should. It maps Rm to the symmetric matrices. And then just the semi-definite condition, we will just write in our partial order notation as x greater equals 0 and the partial order sign. So this means for us that x is a positive semi-definite symmetric matrix. Okay, so then we have the basic framework for our canonical form of a conic linear optimization problem. So we can just state our primal and dual problems. So in our canonical form, gamma was the optimal value of the primal problem, which was to minimize, which is now this inner product again of a given symmetric matrix C with a matrix variable X, and we had some constraints of the form Ax equals to B, but we've given the specific form for our operator A, so we have now this set of linear equations, and then we can just write down the dual. So we know what the dual operator looks like. So the dual constraints become C minus this combination of the A's positive semi-definite, and the dual objective is in terms of the components of this vector lambda. So this is just the inner product in Rm, the usual Euclidean inner product. Okay, so I think many of us are familiar. We call this a standard form semi-definite program, primal, and we call this a standard form dual. And then just now, I just want to understand what does the sufficient condition in our strong duality theorem say for our semi-definite programming problems. So here is the answer. So the answer is, suppose there are numbers, real numbers alpha to alpha m, alpha 1 to alpha m, and the real number rho, so that we can write this linear combination of the data matrices A1 to AM and also the data matrix C, and the result B is a positive definite matrix. And also, if we assume as before that there's a primal feasible plan, then we have the strong duality in the sense that gamma is equal to beta, and there's also a primal optimal plan. So just for the people who are familiar with the Slater condition for semi-definite programming, this is slightly weaker condition than the Slater condition because we also allow this multiplier for the matrix C. So usually the Slater condition just assumes that there is a strictly dual feasible solution or a positive definite dual solution, and this is a slightly weaker condition. So it's good to know. So this is a sufficient condition in semi-definite programming for strong duality, but it's a bit weaker than the usual Slater condition. Okay, so how does one get this condition from this from the theorem on strong duality that we proved? So the thing that we have to remember, the condition in our theorem was that a certain cone had to be closed in the right topology. So so this cone was this thing. This was the image of the underlying cone that we're working on. In this case, a semi-definite cone under this linear operator a hat. And this A hat had two parts. It had this part with the A operator for the primal constraints, and it had this objective part. Okay, so this cone, which was this linear image over all the positive semi-definite of the positive semi-definite cone, had to be closed. Okay, so the nice thing now is that we're working in finite dimensional space, so we don't really have to think hard about what about the topology. It's just a standard topology. But okay, let's just try to analyze this condition from the theorem. And the key thing is that we can just reduce this to showing that this cone is closed to showing that the kernel of this linear operator a hat has a trivial intersection with a semi-definite cone. So basically, the only positive semi-definite matrix that's mapped to 0 by a hat is the 0 matrix. Okay, so the key lemma that we need here is very general, so it does not rely on finite dimensional argument. So I want to state this because we're going to speak in a moment of the generalized problem of moments, and then we of course we have to again be concerned about the topology. So now we have two topological vector spaces V and W in general, and we have a cone in the vector space V, and this is a cone with a special property. It has a so-called compact convex base. So what is the base of a cone? It's just a subset that if you take the non-negative multiples of everything in the subset, then you get the entire cone. So we need such a compact base, compact convex base. So if we just think for a second, what would be a suitable base for the positive semi-definite matrices? Then, for example, if we take the positive semi-definite matrices of trace 1, then this is going to be a compact set in the space of matrices, and every positive semi-definite matrix in the cone is some non-negative multiple of such a matrix. Okay, so definitely the positive semi-definite matrices has such a convex base, a compact convex base. Okay, and the next part of the lemma says, okay, let's consider a continuous linear transformation from V to W, such that the kernel of T has only the trivial intersection with the cone K. So the only element of K that is mapped to 0 by T is the 0 vector. Okay, then Tk, the result is then this image of the cone under the mapping T is a closed convex cone in W. So basically, provided that our cone is special in the sense that it has a compact convex base, and T is a continuous linear transformation with this property that the only thing in the cone that mapped to 0 is the 0 vector, then this image of the cone under the operator T is a closed convex cone. So remember, our sufficient condition for strong duality is that something of this form has to be closed. So here we're going to get this from this lemma. Okay, so let's just do the proof sketch very quickly, and just so the main observation here is the steps that I take are not specific to the semi-definite cone. So these steps are you can apply it to any conic linear optimization problem. The only thing that you have to verify is this compact convex base of the cone that you're working with. Okay, so let's have this compact convex base. Then this T of B, T being a continuous linear transformation, it will map this compact convex base to a convex compact set in W, and 0 will not be in TB because B consists of things in the cone, and the only thing in the cone that's mapped to 0 by T is the 0 vector because of this condition. Okay, and also, sorry, we also have to assume that so the base must have the property that it does not contain 0. So my definition of the base of the cone was incorrect. I had to add that 0 is not an element of the base. So, but my example was correct. So if we take the semi-definite matrices of trace 1, and obviously the 0 matrix is not there, and everything, every possible semi-definite matrix is a non-negative multiple of such matrices. Okay, so the next step is that just to show that the image of K under the operator T is the conic hull. The CO stands for conic hull of the image of the base. Okay, but the cone itself is the conic hull of the base. So I mean, this is not so surprising. It's very easy to show. Okay, and then we just need to show that such a conic hull of a convex compact set is closed to continue, and there again we have a very general lemma that tells us that the convex hull of a convex compact set is closed. So in particular, in general, for a topological vector space, as long as we have a convex compact set inside the vector space, and which does not contain a 0 vector, then the conic hull of this convex compact set is a closed convex cone. So this is then everything that we need. Yeah, so maybe just one word. So compactness. Of course, if we work in this finite dimensional space, this is closed and bounded. So we understand, but in the infinite dimensional situation, if we are only working with topological vector spaces, a set is compact if every cover has a finite subcover. So if we cover any set, if we cover it with open sets, so every open cover has a finite subcover. So one just has to be a bit careful if you're going to use the same argument in the infinite dimensional situation. Okay, so then this is how one derives this more general sufficient condition in semi-definite programming than perhaps most of us are used to. But the main point I want to make is that the argument itself is quite general, as long as we are comfortable that the cone we are working with has this compact and convex base. Okay, so what I would like to do now is move to the infinite dimensional situation, now that we have a little bit of a feeling for the strong duality. Now, instead of working with semi-definite matrices, I want to work with the space of continuous functions and the signed Borel measures. So I just want to remind you that we also had this interesting duality between the continuous functions f, so f being a continuous function on 0, 1, and mu being a signed measure, Borel measure on 0, 1. And this duality is given by the integral of the function with respect to the measure. We have a linear transformation. So for our standard form conic linear optimization problem, which again maps our space that we're working with in the primal to Rm. And again, so we can assume that this is actually given in terms of some given functions f1, so that the measure mu is mapped by A to this collection of components, the duality of f1 mu up to duality of fm with mu, which is of course just the integral of f1 with respect to mu, the integral of fm with respect to mu. So now these fis are just given data. So these are given continuous functions on 0, 1. So again, a nice exercise, which is just in general. So this is not special either to semi-definite programming or to the generalized problem of moments. It's just that if our linear operator is given in terms of some given vectors and in terms of dualities, then the adjoint operator always takes this form. So in particular, this adjoint maps this m-dimensional vector. So adjoint should go from Rm to the space of to the space of continuous functions. So it just works like this. The cones that underlie our problem are in the primal the cone of positive measures or non-negative Borel measures, and the dual cone are the non-negative functions on the interval, the non-negative continuous functions on the interval 0, 1. Okay, so then we just we have a canonical form linear optimization problem just with this specific data, and then again we are minimizing this duality. F0 is given, mu is our variable. It's a non-negative measure on 0, 1. We have these linear constraints given by some right-hand side data values, real values, and these fi's are given continuous functions. And then the dual problem looks as follows. So in the dual problem, again, we are maximizing, and this duality here is just the inner product in Rm, and this y vector in Rm has components eta I again. So we are taking the inner product of the vector b with a vector y. So in this form, and the eta i's must be such that if we form this function f0 plus or minus the sum of the eta i's fi's, then this result must be a non-negative function on 0, 1. So I just wrote this out. So for any value tau in the interval 0, 1, this function must be non-negative. Okay, so this is called the general problem of moments. So you can see in our context, it's just an example of a linear optimization over a cone. But of course, the underlying spaces are not finite dimensional anymore. So here the underlying space is a space of signed measures on 0, 1, and here these are of course continuous functions of this form. So these of course not finite dimensional spaces. So we really need the most general theory to understand the duality. So for the exercise for the participants is just to repeat this argument that we had for semi-different programming to derive a sufficient condition for strong duality. So basically, if we just assume again that there's a primal feasible plan, so that and also gamma is finite, then so the primal is feasible but not unbounded. Then we have the strong duality and the existence of the primal solution from the strong duality theorem if the following condition holds. So basically, we just need the existence of some multipliers alpha I, so that if we take this linear combination of the fi functions, including the objective function f0, and we come up with a strictly positive function, a function that's strictly positive on our interval, then this is a sufficient condition for the strong duality. So the proof is exactly analogous to the one for the semi-different programming case. The only thing that we have to think about is the base for the cone of non-negative measures on 0, 1, And a suitable base is just given by the probability measures. Okay, so you just have to convince yourself that the probability measures give a compact convex base for the non-negative Borel measures on 0, 1. And then the final thing that you can convince yourself of is that, you know, our restriction to univariate functions on the interval 0, 1 was just for ease of exposition. There's no real reason to limit ourselves in this way. We can work with multivariate functions defined on Rn, and we can in fact replace the compact set in R01 by any compact set in Rn, and the duality theory stays the same. So this is the second thing you can think about for exercises. Okay, and then I'm really happy that Didier is here today, because I have a last word. Is a quotable quote from Didier. Not only did he bring us the cartoons about the SOS and the moment problem, he also brought us the saying about the GPM. Everything can be rewritten as a GPM. So maybe Didier does not remember it, but once I was discussing something with him, and I said that I was quite impressed that it could be rewritten as a general problem of moments, but then Didier said, oh no, everything can be rewritten as a GPM. So this also brings us, this is a good way to bring us to the second part of my tutorial. So just to get started. So for the second part, I'm going to talk specifically about one application of GPM, but as you can gather from Didier's comment, there are many more. So let me just switch. So maybe Felix, can I just check that you see this outline?
Yes, we can.
Okay, great. So now I continue with one specific application of the general problem of moments, and this is a problem from approximation theory, and it's called uniform approximations using the generalized problem of moments. So the problem that we are talking about is perhaps the most fundamental in approximation theory. Is we are given some continuous function g, again on let's say on 0, 1 for ease of exposition, so just the function continuous on 0, 1, and we want to approximate this by some other given continuous functions on 0, 1. So more generally in approximation theory, one is interested in approximating a given function from some finite dimensional function space. So you can view these as spanning some finite dimensional function space, and we want to get the best approximation of a given g in some sense from this function space spanned by these functions. So what this usually means is if we want to do uniform approximation, we look at the difference between g and some linear combination of the fi's in the infinity norm. And the infinity norm is just the maximum absolute value of this function taken over the entire interval. Okay, so notice that, you know, everything is nicely continuous. So we have this function is continuous. So the supremum on the interval is attained. So we can write the maximum. Okay, so this is just the idea. So we try to find the best approximation of a given continuous function from a finite dimensional function space. Okay, so just to our notation, this was the CO1 was the space of continuous functions. So in words, we want to find the best uniform approximation of the function g in terms of this set of functions f1 through fm. Yeah, okay, so once again, like I just mentioned for the generalized problem of moments, this restriction to the interval 0, 1 is a bit artificial. It's just for ease of exposition and drawing some pictures. But I mean, the same analysis works for compact sets in RD. So we could have started with a given function which is continuous on some compact set in RD, and similar for these FIs and ask the same question, and everything that I'm going to discuss also works for the more general situation. So this is just the 0-1 interval is just to fix our ideas and make the exposition a bit simpler. Okay, so let's do a picture. So let's say we are given this function g on 0-1, given by the function 1/3 the exponential function, and then it looks something like this. Yeah, so here it should be 1/3 e, and yeah, so that looks about right. Yeah, and here it should be 1/3. Yes, so that is its function, and then we want to approximate it by some polynomial of degree at most 2, because we are allowing linear combinations of the standard monomials of order up to 2 for a univariate function. So basically we can construct any polynomial of degree at most 2 we want to try and approximate our given function. So here is one possibility in red. So it's doesn't look too bad. So it's 1/3 plus 1/3 tau plus 1/6 tau squared. And then we have another something we can do with the blue one, where the coefficient of the quadratic term is in fact e minus 2/3. So it's a bit different from 1/6. And you can just see visually it's a much better uniform approximation than the red line. Yeah, so but the question is then, is it optimal? So you know, it seems to be quite a difficult problem to decide whether a given approximation is an optimal uniform approximation. So our goal here in this hour is just to try and understand the you know, how we can rewrite this as a conic linear optimization problem, and then we have some tools from our toolkit to try and solve such problems. Okay, so let's just think about the reformulation of our uniform approximation problem as a conic linear program. So I'm going to minimize some scalar variable psi0, and then I'm going to kind of enforce by these two conditions that psi0 is greater equal than this absolute value for all tau. So which just means that psi0 will always be greater equal than the infinity norm of the function g minus this function here. So for the given psi values. So basically these two conditions just ensure that psi0 is greater equal that the supremum norm or the infinity norm, whatever you want to call it, for these given values of psi. So, and we are trying to find the best possible values of psi. So if we minimize this psi0 and it's greater equal to the supremum norm, then obviously we are doing what we want. We are finding the smallest possible supremum norm of the error. So this is the best uniform approximation. Okay, so that's clear. Yeah, so basically this trick is familiar to everybody because yeah, so if we want to minimize absolute values, sums of absolute values in linear programming, we use this kind of tricks to bring it to a kind of linear programming problem. So this is a familiar trick, I think, to everybody. Okay, so now the next thing is we want to rewrite this as a conic linear program, because if we just look at this, then it's not in the form that we discussed so far. But obviously we have some non-negativity conditions on the interval here and also here. So this we can interpret as something belonging to the cone of non-negative continuous functions on 0,1. So you can see all the elements are there to write it in the conic linear optimization form. And so just now we just recall the setup from the first part of this tutorial. So we had these dualities for these spaces 1 and 2, and we had these cones, if you remember, defined by the respective dualities, and they also had dual cones. And then we also had the A operator that gave us some constraints on the primal problem, and it had an adjoint operator, which we remember this trick that if we move the A to the other side, it becomes A star, and the duality changes. okay, this was our setup from the first part. So exactly the same thing. And now we just have to kind of identify our approximation problem with each one of these spaces and dualities. So we have to specify what is duality 1, 2, what are these spaces, how does our operator A look like, how does our operator A star look like. So basically we just have to identify the special case. Okay, so so our general primal problem was in this form. So remember, later on we assumed the canonical form without loss of generality, where K2 was just the zero cone. So then this became AX is equal to B. But I said that in some cases it's useful to have the more general setup, and for us this is going to be useful now to have the more general setup. Then for the general primal problem, we saw the general dual problem took this form. So the dual objective was in terms of the second duality. The dual constraints had two conic constraints. The dual variable L had to belong to the cone K2 star, and C minus A star L had to belong to the cone K1 star. Okay, so we have a lot of terminology here, and so we just have to fill everything in to obtain a conic reformulation of our approximation problem. Okay, so I'm just going to go through this, what all these spaces are, and then we try to just convince ourselves. So we're going to have the E1 F1 space is the same, namely Fm plus Rm plus 1, with the duality just being the Euclidean inner product and Rm plus 1. We're just going to have this, the E2 are kind of pairs of continuous functions on 0, 1. Our space is a space of signed Borel measures, and as before, and our vector space V2 is going to be this direct sum of two copies of the Borel signed Borel measures on 0, 1. Okay, so we're going to have a duality. The second duality is a duality between E2 and F2. So E2 are these pairs of continuous functions, so like H1 and H2, and then F2 are kind of pairs of signed Borel measures, and mu1 and mu2, and then we're just going to define this duality as the integral of H1 with respect to the measure mu1 plus H2 with respect to the measure mu2. So again, one has to, of course, verify that this is indeed a duality, but this is a straightforward exercise. So then we also have a linear transformation that maps E1 to E2. So let's just check it must map Rm plus 1 to this space C plus C. So we are mapping Rm plus 1. So we have m plus 1 components, xi 0 up to xi m, and we are mapping it to a pair of continuous functions on 0, 1. And these are just the same function. And then the cones that we have. So one of the cones is just the whole space, and the cone K2 are pairs of non-negative functions on 0, 1. So okay, so my claim is just if we fix all the spaces and dualities as this and the operator A, then we okay, sorry, but there was one last thing, that we have a right hand side vector B for the primal constraints, and this is just given by some element in E2, so it has to be a pair of continuous functions, and G is just a given function that we are approximating, and then we also have minus G. Okay, so then we have the vector B, and then for the primal objective, so then we are talking about Euclidean inner products for the duality 1. So this is just the vector with first component 1 and then m component 0. Okay, so that's a whole mouthful, but then if we've done that, then our uniform approximation problem, which we had before, just reduces to the standard form of primal problem. So so let us just do a reality check here. So if we just compare these two things, so the objective here is just psi 0, the first component of a vector, let's say vector x with components psi 0 up to psi m. So just to get this the same objective here, we remember that the one objective, the one duality was just the Euclidean inner product of C, which is the standard unit vector with the first component 1, and the psi vector. So indeed, this is correct. So this is as it should be for the duality that we define. And then these two conditions here, they will correspond to this ax or b, ax minus b belonging to the set to the cone K2, and the cone K2 were just pairs of non-negative functions. Okay, so basically we will have two non-negative conditions. So if we bring b to the right-hand side to get ax minus b, then the b vector obviously has to be g and or minus g and g. And if we just go back here, it was or g and minus g. So that's as it should be. So then basically the ax part has to correspond to this part right here. Then we just have to look at how we define the a part. So indeed, this was this part, and we just recognize it here and with a minus sign here. Okay, so indeed this is like this. And then the final thing we have to do is x, our vector psi 0 to psi m, must belong to the cone K1. So so what is the cone K1 again? Okay, this is just Rm plus 1, so there's no further restriction, so we just can write it like this. Okay, so that's a bit technical, but not difficult. And then we can also write down the dual problem. But so we had our operator A. So to write down the dual problem, we need the adjoint operator. And the adjoint operator maps pairs of measures to Rm plus 1. And one just has to verify as an exercise that this adjoint operator maps to given measures mu1 and mu2 to this vector of length m plus 1. Yeah, so we integrate here the function 1 with respect to the measures mu1 and mu2, and then everything f1 up to fm, and here we take the difference, and here we take the sum. So this is a little exercise, but again, it's not difficult. We just have to verify that for this given operator A star, the condition for the adjoint is satisfied. Okay, so then we also need the dual cone. So the dual cone are just copies of non-negative measures. So we have it's a dual of pairs of non-negative functions, and this is precisely the pairs of non-negative measures. Okay, so then we have the dual problem. So the dual problem again is A star L or satisfies this condition, which means C minus A star L must belong to the cone K1. A star, we have L must belong to the cone K star, and then as we did with the primal problem, we just have to interpret it, and then what we get is the following dual problem. So so basically, just to remind ourselves, so this L belongs to the space F2. So the space F2 talks about the pair of measures. Okay, so this to remind ourselves, this L it belongs to space of pairs of measures. So that's why we have as variables the unknown measures mu1 and mu2. But this also has to belong to this cone. So these actually have to belong to the cone of non-negative Borel measures on 0, 1. So, and let's just look without further verifying. This is just it's easy for you to verify that this is the correct dual. But you see, what we are doing is we are maximizing the integral of g with respect to the measure mu1 minus the integral of respect to the measure mu2, and then basically the sum of the two measures equals 1, the measure of the function 1. And then we have these conditions that for each I, the sum of these two integrals has to be 0. Okay, so obviously, yeah, so this is clearly recognizable as a generalized problem of moments. So on the moment side. And now the next thing I want to discuss is what does strong duality look like? So so basically, you know, for the canonical problems, we had this result that we will have strong duality if a suitable cone is closed in the weak topology of the duality. So let's just look at what does this look like here. So one can show that for this uniform approximation problem, the primal and dual optimal values are equal, and moreover, there is both a primal optimal plan and a dual optimal plan. Yeah, so let's just quickly go through the idea of the proof. So the key result is, of course, the strong duality theorem that we had in the first part, so we need that the cone we work with is closed, and we need that it has a compact base. So the thing that we have to show is that, you know, the non-negative Borel measures on 0, 1 has the compact base given by the probability measures. Yeah, and the existence of the prime optimal plan means that the best uniform approximation exists. So the problem is really well defined in that sense. Yeah, and the interesting thing is one can also show that, you know, the optimal dual solution, which consists of these two non-negative measures, mu1 and mu2, we can actually show that these are atomic measures. So they are conic combinations of Dirac delta measures centered in 0, 1. So the optimal solution is actually interesting. These measures are actually atomic at the optimal solution. So for those of you who know Chakalov's theorem, and so this will not be surprising, but one can also just think of this in terms of a generalization of the Kara-Theodoris theorem, that that, you know, the extreme points of the probability measures on 0, 1 are actually the Dirac delta measures. So in some sense, if you can use an infinite dimensional analogy of the Kara-Theodoris theorem to argue that, you know, your solution is given in terms of as a convex combination of Dirac deltas. Okay, so then I just want to at least spend a few minutes after discussing all these classical topics, just to give an example that I'm actually working on with some people, so some current research, and the whole idea is to try and generalize a very classical concept, namely that of Chebyshev polynomials. So I think Chebyshev polynomials are probably the most famous family of orthogonal polynomials, and they are defined on the interval -1, 1 usually in this way. So it's defined in terms of trigonometric functions, but on the interval -1, 1, these coincide with polynomials, because you can show recurrence relation that the k plus 1th Chebyshev polynomial is obtained from the two before, so from the kth polynomial and the k minus 1th polynomial, by taking 2x times the kth one minus the k minus 1 polynomial, and where we're just setting the -1 polynomial equal to 0. And of course the t0 is just cosine of 0, so it's just 1. So the first Chebyshev polynomial is just 1 on the interval -1, 1. And then if we use this and the recurrence relation, we find that the first one is the line t1x is equal to x. The second one is this parabola 2x squared minus 1. And the third one is this polynomial. So something that you would notice is yeah, okay, so this okay, so these are the first four Chebyshev polynomials, but and you know, so the Chebyshev polynomial tk has degree k, so t0 is degree 0, 1, 2, 3, etc. And obviously so these define the basis of the univariate polynomials up to degree k. If you list the first k Chebyshev polynomials, so these polynomials have many beautiful properties. But I want to just remind you of one specific property, and that's quite interesting. So of all monic polynomials of degree k greater than 1, so then this Chebyshev polynomial, where we just make it monic by dividing by the right number, has the smallest supremum norm on -1, 1. So basically these TKs lie between -1 and 1. So the supremum norm of TK is always 1. So the supremum norm of this times 2 to the k minus 1 or divided by 2 to the k minus 1 is just 1 over 2 to the k minus 1. So this is of all monic polynomials of the degree k, this has the smallest supremum norm on 0, 1. So then, you know, this just means that we can if we are interested in a specific uniform approximation problem where we approximate the monomial x to the power k for some fixed k, and we approximate it by polynomials p of degree at most k minus 1, so degree 1 less, then the answer should be xk minus p star is equal to, and I forgot this factor to make it monic, so I should have taken this factor to make it monic. Okay, but basically, so because, you know, this thing inside the argument is going to be a monic polynomial of degree k. So if you think about it like that, we are minimizing its supremum norm, and we know that the polynomials of degree k, monic polynomials of degree k with minimum supremum norm is of this form. Okay, so I should just fix this to make it monic. Okay, and then of course this gives us an idea about how to generalize Chebyshev polynomials to the multivariate case. So just a few words. So why is this necessary? Isn't this completely classical? I mean, the point is that there is no one way to generalize Chebyshev polynomials to the multivariate case. So the simplest way is just to multiply univariate Chebyshev polynomials together, and then you get multivariate polynomials that have orthogonality properties and so on with respect to the right measure. But the thing is, then you don't get really a basis in the multivariate space because you have too many of these products of univariate Chebyshev polynomials. You just get a spanning set. Yeah, so it's and also it depends. You know, we start on -1, 1 in the univariate case, but it depends a lot on the set, compact set in Rn where we want to define generalized Chebyshev polynomials. So it is not a simple. There's no simple answer to how to generalize the Chebyshev polynomials to the multivariate case. So, but obviously, what we could do is we can just mimic this, and we can consider this uniform approximation problem. And instead of looking at x to the k in the univariate case, we can look at x to the alpha for some monomial. So now x to the alpha is just a monomial, x1 to the alpha 1 up to xn to the alpha n in the usual notation. And now we are looking for some polynomial p of n variables of total degree at most k minus 1. If the sum of these alphas are k. So basically we have a monomial x to the alpha given, and the degree of this monomial is k, and we approximate this to the uniform approximation problem of is x to the alpha by polynomials of degree at most k minus 1, total degree at most k minus 1. And then in some sense, in this sense, the answer should in some sense correspond to a Chebyshev polynomial, at least in the univariate case. If we do this in the univariate case, the answer, this whole argument inside, will be the constant multiple of the Chebyshev polynomial. So if we do it in the multivariate case, we get some generalization of the Chebyshev polynomials. Okay, so then obviously we can define, if we want, some generalized Chebyshev polynomial as, you know, whatever the answer is, x to the alpha minus this optimal p, which we will call p star, and then this is our generalization to the multivariate setting on this compact set K in Rn. Okay, and then so then I have an example. So like I said, I'm working on this with some people in the context of a project at the American Institute of Mathematics. Marike Dressler, Simon Foucault, Yara Yildiz, myself, Jean Bernard, and Professor Xu, I forget his first name now. So we're just looking at some toy examples, but this is an interesting one. So one set where we can generalize the Chebyshev polynomials to is a simplex, the full dimensional simplex. So let's just look at the simplex in R3. So this consists of these components x1 to x3, sum is at most 1, and these are non-negative variables. So just the full dimensional simplex. And we can just think about some specific monomial to approximate, namely x to the alpha. And so alpha 1 is 1, alpha 2 is 2, alpha 3 is also 2. And this is basically the simplest case, as I understand from the approximation theories, where the best approximation is not known. So we're going to give the best possible approximation using a polynomial of degree 1 less. So 2, 3, 4. So we need the approximation of degree 3. Okay, so then what we did is we used the so-called Lasserre hierarchy for the generalized problem of moments. I will just talk briefly about it on the next slide to solve this approximation problem, where p the approximant p has to have degree 1 less. So again, k here is 4, so we are limiting ourselves to p of degree at most 3. And you will see, so the approximate solution that we get numerically is this degree 3 polynomial. And you can, if you stare at it, it has some symmetries that we expect, like this thing is symmetric in x1, x2. So basically the x1 squared and x2 squared should have the same coefficients and so forth. So basically also this the symmetry between x1, x2. So we have the same coefficient here. And then so basically x to the alpha minus this thing gives us a generalized Chebyshev polynomial in 3 variables corresponding to this x to the alpha on the simplex. Okay, so this is an ongoing project, so I just use this as a small example, and maybe I just want to finish more or less by just saying something about this Lasserre hierarchy that we use to solve a generalized problem of moments, because I mean this is one of the only tools available to really numerically solve generalized problems of moments. So this is actually quite interesting to look at this. So so basically now if we are doing this approximation on a set K, we just assume that we can describe it in terms of constraints. So if in this case, obviously we had these constraints, and we can just rewrite them in the form some polynomials greater equals 0. So this is obviously the case here, but in general we just assume such a semi-algebraic set K, and we also need it to be compact. Yeah, so and we just specify a general function f that we want to approximate. So I guess f should be a polynomial that we want to approximate of degree k, just to be consistent with our previous notation, and we approximate it with something of degree k minus 1. Sorry, so this f is just something we want to approximate. So in the previous example, it was x to the alpha, a monomial, but we can just make it a general polynomial of total degree k. And then our this relaxation due to Lasserre is a hierarchy, and you will recognize our reformulation of the uniform approximation problem. The only thing is that we had this condition here, is that this function on the left-hand side had to be non-negative. And this is relaxed to, this non-negativity condition is relaxed to some Putinar type condition, that instead of being a non-negative polynomial on the set k, we say it can be written as a sum of squares plus sums of squares times the gj functions, which are non-negative on k. So obviously, if this thing is of this form, then it's non-negative on k, but I mean, the converse is not necessarily true. And then basically we get the hierarchy indexed by t, but by allowing larger and larger degrees of these sums of squares polynomials. So basically, on the tth level of the hierarchy, these sums of squares, sigma 0 and psi 0, have the degree at most 2t, and then these ones here have degree at most 2t minus the sum of the degrees of g. So basically, just so that the product here has also degree at most 2t. So these then give us upper bounds on the smallest supremum norm in the approximation, and as t goes to infinity, this converges to the best uniform approximation norm. So the interesting thing is, so we actually get feasible approximations from this. It's not just this is actually, we get upper bounds. So every solution here, if we have these functions p and sigmas and psi's, then this p is some approximation to f. Yes. So this is something that's just worth noticing. It's a little bit different from the polynomial optimization situation, but anyway, these values, they do converge to the minimum value of the approximation of the uniform approximation. Okay, so then that was basically what I wanted to say. And then later this afternoon, there will be an exercise session. I'm not quite sure how we will do this yet, because when we planned this, we were still hoping to meet in person in Tilburg. But I just give some exercises already that you can think about. So in addition to the ones we've already had. And then at the end of the afternoon, those of you who still have some stamina, we can discuss together to see how to do these exercises. So just to get back to our original example. So we said that the blue approximation is better than the red one, but how can we try to decide using duality theory if this is optimal? So let's try to understand if this blue function is actually optimal by using duality theory. So we have on the one side we have a feasible solution, this function. And the dual side, we have to find a suitable pair of non-negative measures such that the duality gap is 0, and then we will know that it's optimal, or maybe it's not. So I don't even know for sure, but we're going to figure this out. And then maybe just the last thing. So just to for those of you who would want to know more about this topic, so as I said already, this book by Barvinok is a wonderful resource if you want to understand convex duality in more detail. This Lasserre hierarchy for the generalized problem of moments appeared in this paper in mathematical programming. So Monique Laura and myself, we have a survey of these SDP approaches to the generalized problem of moments in this volume. And then, of course, also Jean Bernard has a couple of books specifically dealing with these generalized problems of moments and the applications. So this is very, very much worth reading So like I joked with Didier, there are many applications, including like options pricing in finance and whatever. Polynomial optimization is a special case of the generalized problem of moments. So it's a very, very rich problem. So it's if it's interesting for you, you can find a lot of information in the book of Jean. Okay, so then I thank you very much for your patience, and I will hang around to take questions if there are any. So you can just put them in the chat, or you can just unmute yourself and ask. Thank you for. I see some applause at least. Thank you very much for that.
Sorry, can you hear me?
I can hear somebody.
Yes, sorry, I have a question. Do you know, in the case of a cube, when you have your compact set to be a cube in n dimensions, do you know if the product of Chebyshev polynomials, like of respective degrees of univariate Chebyshev polynomials, gives you a solution, or it's not the case?
So a solution to what?
So you have your monomial, let's say x1 squared times x2 to the cube, okay? And then the question is whether the product of first and second Chebyshev polynomials, respectively in the variables x1 and x2, solves your generalized problem.
Yeah, I think this is indeed the case. I just have to check it, but I recall discussing this with my colleagues in approximation theory. So indeed, I think the approximation problem on the -1,1 hypercube is settled. So that's not really an interesting case.
I see. In this formulation, right? The one you gave. Okay.
Yeah. So because yeah, indeed. So because if you just want to approximate x to the alpha on the -1,1 hypercube, then you can first write x to the alpha in the Chebyshev basis, right? Yeah. Yeah. I mean, of course, it's a natural question, but I will have to check. Maybe I can get back to you. I mean, this is I do believe this is indeed an easy case, the -1,1 hypercube, the approximation.
Okay.
I mean, let me just make a note. I can get back to you.
Okay, thanks.
Yeah, sorry. Just I think you also asked yesterday something about the complexity of minimizing a form on the unit sphere. Is that correct?
Not complexity. I was asking about like checking convexity, right?
Oh, convexity. No. Yeah, no. Yeah, but yeah. So yeah, indeed. So you can yeah. So there is yeah. Okay. So then I understand. So then you have a kind of a form in two sets of variables, right? So if you're checking the Hessian is non-negative, it's on a bisphere. Yeah. So yeah. Okay. I can send you a reference. I not a complete answer, but I also have a reference where at least this is discussed.
I see.
So I have two things: the hypercube and the convexity of forms on the sphere.
Ah, great. Thanks.
Okay, so it has fallen quiet. Oh no, Monique, please.
Sorry, Etienne, can I ask a question just for my understanding? So these generalized Chebyshev polynomials on a set K, so you define them via approximation. So yes. you don't have any orthogonality conditions anymore, or do you?
No. I mean, this is the thing, the Chebyshev polynomials have many nice properties, but if you are generalizing, you lose some properties. So so this is, we are only trying to keep now this property that you have minimum supremum norm among monic polynomials.
Okay.
Of this degree.
Okay. So the beautiful thing on the univariate case, or the cube, but it's clear, was that they were orthogonal. They had these two features, orthogonal and this, but this doesn't go anymore when you generalize. Okay. Thanks.
I see someone else is Bernard.
Hello, Etienne.
Hello.
Nice presentation. So the question also about this multivariate Chebyshev, and can they be used to have good approximation of functions, as in the say the univariate case?
Yeah, I know these are natural questions, but I mean, you know, my interest is really on the level what I discussed. So I mean, I work with these people from approximation theory. They are interested in these constructions, but you know, what you can actually do with them, I'm not so up to date.
Okay.
Yeah, I think, you know, usually with approximation, whether it be univariate or multivariate, this orthogonality property that Monique mentioned is very crucial. So I mean, I don't really see why, you know, this would be specifically interesting for approximation.
So I think in the univariate case, they give almost the best
Yes.
Approximation of a given function.
Yeah, so I mean, yes, so they are kernels like Jackson kernels, and so it's constructed in terms of Chebyshev polynomials. Yes.
Mm.
Yeah. So the Jackson theorem says that, you know, what is the best possible approximation of a given degree, and then the Chebyshev construction with the Jackson kernel matches these approximations. Yes.
Yeah. So. My question was if this could be also extended in this.
Yeah, you know, this is like I discussed just with Monique. So the thing is that, you know, if you keep one property, you lose some others. So I think these are very difficult questions. So I mean, the multivariate approximation that I know of with Chebyshev polynomials, and actually Felix will speak about this on Thursday. You know, then we are just basically taking products of univariate Chebyshev polynomials to do these constructions. So then we are just working not with the basis, but just with some spanning set which has nice properties. But,
okay.
But I would encourage, I mean, if you're interested in this topic, Felix is going to give a talk about this on Thursday. So precisely about this topic.
Thank you.
Thank you, Bernard. And Felix is smiling. Okay, so let me just see. Thank you, Monique. And so then I think if there's nothing else, we have some lunch. And in the afternoon, Juan Vera will take over to chair the two talks in the afternoon. So thank you very much for your attention. And those of you who are interested, we can meet later in the afternoon for the exercise class. So thank you very much and see you later.